be talking today about temperature-dependent characterization for device research and development. The outline for my talk today, we're actually going to start with two questions, and hopefully questions our audience have been trying to answer themselves. The first of which is, why do we want to do temperature-dependent device characterization? And the second question is, why probing? After we delve into those two questions, we'll basically take a look at the anatomy of a cryogenic probing platform to do temperature-dependent device characterization. And finally, we'll discuss some applications using the Keysight B1500A to do cryogenic and variable temperature device probing applications. So we start out with that very first question, why temperature-dependent characterization? And we really have and see four basic themes for looking at devices and materials with variable temperature measurements. The first of which is defect identification. And so at cryogenic temperatures, we see in a lot of devices and materials that defects become much more prominent in the electronic signatures and in the measurements that you take at those. For example, Schottky barrier leakage, and that's what we're showing here. It's just a Schottky barrier. And, at cryogenic temperatures, the thermionic emission goes down, and you enter into a tunneling regime at cryogenic temperatures. And so defects and trap states, at that barrier can assist in that, and there are signatures that go along with those trap states. And so defect identification is a really important and key approach for doing cryogenic and variable temperature measurements. The second reason that folks do temperature-dependent characterization is that the devices themselves need to operate in extreme environments. And so devices that need to operate at really high temperature, and in our cases, at very low cryogenic temperatures. And so the example we give there is of radio wave astronomy, and the photo is of the Arecibo facility in Puerto Rico. Third reason we delve into temperature-dependent characterization is to improve the device performance. And so defects we associate with material properties, and we can also look at how a device architecture is affected by temperature. And so in this case, we're just showing some drain current measurements there for a silicon JFET. And what we see is just as we cool down, we have a much improved on-off ratio at cryogenic temperatures, and correspondingly a smaller leakage. And this just has to do with the leakage effect in the substrate used for those devices. The final reason that we use variable temperature dependent characterization is that there's just emergent phenomenon. So as you lower the temperature of a device or material, things like superconductivity can occur in certain materials, and other materials there's phase transitions. And so we can use those physical phenomena for certain device applications. Now, before we kind of delve into the idea of device characterization, we want to take a step back and really get a sense of how material properties influence device performance, especially at cryogenic temperatures. So what we're looking at here on the slide is a photo or a graph of the Hall mobility of indium phosphide taken over a range of temperatures. And what you see is that room temperature on the right-hand side of the slide, we have a lower mobility, and as we cool this indium phosphide material down, the mobility steadily increases, and then as we cool closer to cryogenic temperatures, we actually see a decrease in the Hall mobility of this material. And sort of the way we want to understand this is at high temperatures, the carrier transport is dominated by lattice scattering, whereas at low temperatures, the carrier transport in this material is dominated by impurity scattering. I'm a big fan of physical pictures and getting really a microscopic view of what's happening inside of materials and other physical systems. And so what we're looking at here is a little animation of an electron traveling through your favorite semiconductor material. And so the electron, as it's traveling through your semiconductor, is in fact in the presence of a lattice, and that lattice is vibrating, and the vibrations basically are tied to the temperature of the material. And so the picture that I like to have is that at low temperatures, the carrier really sees much more smooth and calm waters. If say, for example, it was paddling across the lake, but at higher temperatures, those waters get a little bit more choppy due to the vibrations in the material, and so transport gets a little bit harder. Thus, we have lower mobility at higher temperatures. Now, defects become more important as we cool to lower temperatures, and so that in our animation now we have the presence of a defect which our carrier can scatter off of. And so in our analogy of paddling across the lake, lower temperatures, those defects can in fact become much more apparent, much harder to paddle across. Now if we were to add some temperature to this, some waves on top of those defects, we may not actually in fact have as difficult a time paddling across that lake with some waves going on there. And so as we talk about cryogenic temperatures and electronic transport properties, the basic idea that you need to come across with is that scattering from impurities and phonons are going to induce random fluctuations in the resistance. This is actually a well-known phenomena. It's the Johnson noise in a device, and you see down there in the lower left-hand corner of the equation where the voltage noise is proportional to the square root of temperature. And so as we cool a device down, in fact, the voltage noise in that device should get smaller. And this is actually the reason why cooled microwave amplifiers are used in many radio astronomy applications. So now that we have sort of this flavor for doing variable temperature transport property measurements, we move on to our second question, which is why probing? So probe stations basically offer a flexible electrical measurement platform that first offers wafer level characterization. And so by probing or measuring the device at the wafer level, we avoid the time and cost of doing the packaging. That includes dicing your wafer, wire bonding to the device pads, mounting the device in a package, and then finally, in the case for cryogenic characterization, cooling the device down. There's a lot of steps and a lot of time and cost added by packaging devices. Probe stations allow you to get around that, and in fact, basically make temporary electrical contacts to a wafer level device. For lakeshore cryogenic probe stations, these are manual probe stations designed around doing research-grade characterization. So in a manual probe station, you're going to independently move each of the electrical probes using a micro-manipulated stage to each individual device pad. So these research-level measurements are really built around doing few device characterization. And so this is what you encounter for research-level characterization, where you're trying to tune a material property, you're trying to tune an architecture. So we're not making thousands of devices, we're making few devices, and we want to characterize those devices typically over temperature. Now, once the research stage on device development, we're passing out of that and we start moving into the development phase. Oftentimes we have wafers that get larger, or in fact have a larger number of devices. And so for those larger scale characterization applications, Lakeshore has partnered with Cascade through their Measure One initiative to offer our customers, our mutual customers, semi-automated cryogenic probe stations which offer vacuum and again cryogenic characterization for larger scale wafers. And so these wafers can be probed up to 200 millimeters in diameter.
So in addition to wafer level characterization, device visualization is another reason that researchers use probe stations for device measurement. Visualization can be particularly important for optoelectronic applications, as well as for MEMS and piezoelectric characterization. So here in this slide, I'm showing a probe PZT membrane, which is flexing as the voltage to the device is modulated. Now, because we could see this device under operation, we're able to observe clear changes in both the amplitude as well as the structural modes as this device was cooled to cryogenic temperatures. Finally, researchers use probe stations because of the unparalleled flexibility for controlling the device environment during a measurement. So probe stations often can be configured to change, say, the surrounding atmosphere and or temperature of the device, apply an oriented magnetic field to the device, or illuminate the device during measurement. Now, because environmental control is a key factor for device measurements, Lakeshore is offering a wide range of liquid cryogen as well as cryogen-free probe stations. Lakeshore magnet probe station models, they're going to offer the ability to apply a magnetic field in a direction which is either horizontal, which is in the plane of the device, or vertical, that is perpendicular to the device. So in addition to, say, magnetic field, our probe stations can be configured with fiber optic probes, low leakage guarded cabling, so as well as RF and microwave probes up to 67 gigahertz. Now, to better understand the challenges which are inherent to device measurements in this cryogenic environments, we're next going to take a look at what goes into building a reliable cryogenic platform.
For device characterization, typically what ends up happening is we're going to mount our device to a sample stage. In most cryogenic probe stations, we're able to cool that sample stage down to around 4 Kelvin. With the addition of our ultra-low temperature option in a few of our stations, we can cool that stage down to temperatures as low as 1.6 Kelvin. With the addition of our high temperature stage option, we can heat a device up sample stage up to 675 Kelvin. So in a cryogenic probe station enables the user to basically characterize a device over a really wide range of temperatures. So we've mounted a device to our cooled sample stage. In order to keep that device temperature at a well-known value, just a lot of things have to go around the sample stage. The first of those is actually our radiation shields. So we surround the sample stage with a series of radiation shields, reducing the radiative heat load that a device sees. It's critical in order to maintain that device temperature while we're doing temperature-dependent characterization. Next, there's a vacuum chamber. So we've surrounded our radiation shield and sample stage with our vacuum chamber, which we have to evacuate the probing environment. Now, this is a necessary step for cryogenic operations, but it's also advantageous for surface-sensitive devices. So for those devices which their properties would change when exposed to ambient conditions, the vacuum environment offered in a cryogenic probe station can be really helpful. For certain Lakeshore cryogenic probe stations, we've also added a load lock option. And so a user or researcher can put together a device in a glove box or a dry box and transfer it from that dry box into our cryogenic probe station without the device ever seeing ambient environment. The final piece of our cryogenic probe station is the probe arm itself. This is a micro-manipulated stage for which we add our wires or our fiber optic probe cabling to, and then those probe arms are actually thermally anchored to further reduce the conductive heat load that a probe device is going to see. On the end of our probe arm, we actually can functionalize it in many different ways with different ranges of cables and probes. Those probes can be either a DC probe, a microwave GSG probe, our fiber optic probe arm option, and most recently we've offered and released our Terraris probe arm for on-wafer characterization up to 220 gigahertz. What we're going to do today is focus on just a handful of DC probing applications, and what we're going to start with is our IV measurements. So for cryogenic variable temperature transistor or IV measurements, basically need to look at two aspects of the measurement. The first is the thermal aspect, and the second is going to be the electrical aspect. So for a good cryogenic transistor measurement, we need to look thermally at having good device contact to the thermal chuck. Now, depending on your device, the substrate material, and as well as many other experimental aspects, we can attach that device using either end grease, silver paint, or paste, a thin cyanoacrylate glue, carbon paste, or mechanical clamping, among others. In addition to having good thermal device contact to the chuck, the thermally anchored probes, as I said, are going to minimize the heat load on the device, but those thermal anchors can be configurable for various operational conditions. So at the right, we show is basically the device offset temperature compared to the sample stage temperature. And what you can see is for that particular configuration, we're able to maintain the device to within 2 Kelvin of the sample stage temperature over the entire device measurement range. So from 4 Kelvin all the way up to 300 Kelvin. In addition to the thermal aspects, as we mentioned, the electrical aspects of the measurement become important. Lakeshore probe stations offer multi-terminal probes, so we can add up to 6 independent micro-manipulated probes to our probe stations. For transistor measurements, we recommend a triaxial configuration for low current measurements. So our vacuum feed-throughs are 3-lug triaxial measurements, and so those interface well with the B1500 SMU. We offer guarded measurement from the analyzer all the way down to the DC probe. And finally, we offer an optional triaxial sample stage, so you can do guarded backside device contact. The graph on the left or on the right there basically shows our the femtoamp level leakage performance of our probe arm. Both the thermal and electrical aspects of the measurement are critical for a good transistor measurement. So what we're showing here is just the cryogenic temperature pHEMT measurement. So for one of these measurements, what you see is B1500 there, and then we mount our device to the sample stage, and then bring those probes into the device contacts. In the photo that's shown here, the dimensions of each of those pads, the width of those pads, is about 70 microns. So we've cooled our device to cryogenic temperatures. We've landed our probes onto the device. Now we use a B1500 to do an IV sweep, and so we use the IV sweep test definition for this particular device. You can see here we've added a little bit of analysis to that, and so what you can see is that we have a pinch-off voltage sort of around 750 millivolts, as well as just an idea of the subthreshold slope. Now conventionally, for a cryogenic device measurement, we land our probes at a given temperature, and then before we move to the next temperature, what we're going to have to do, we would have to lift those probes, move to the next temperature, let the sample stage come to equilibrium, and then re-land the probes onto the devices. For a device measurement over a wide range of temperatures with reasonable temperature sensitivity, it actually results in a large number of lifting and re-landing cycles. It's actually pretty inefficient when it comes to doing a device scale measurement. Lakeshore has offered now a continuously variable temperature probe. It's a flexible DC probing option, which basically allows the user to land the probe on the device at low temperature and then perform an automated temperature-dependent device profile. This patented device design of probe basically has a spring member in there that allows the probe arm, as it's warmed up, to thermally expand without causing the probe itself to slide off of the device contact. So that's what we're showing on the right there, is that with our standard probe, that device contact would be lost because the probe arm is going to expand as it warms up. And with our CVT probes, that expansion is basically taken care of by the flexible spring member in that device. Depending on your probe station, the range of temperatures can be that the device or the probe can operate over will vary. And so it's important to choose a probe station and the CVD probe depending on your measurement application. So now we have a flexible probe and we can maintain contact with the device. We now want to start considering the ability to do automated variable temperature characterization. So this is where, in conjunction with Keysight as a solution partner, Lakeshore has put together an interface between the measurement power of the B1500 and the Easy Expert software interface and our temperature and magnetic field dependent capabilities that we offer in our probe stations. And so using test definitions as well as the GPIB interface available on the B1500, we can now use the B1500 to control both temperature and magnetic field for a measurement. As I said, we use an integrated test definition on the B1500 in Easy Expert. And so the way that this operates is that the test definition is going to do a controlled ramp to a temperature set point. The control parameters that the temperature controller are going to use to bring the stage into thermal equilibrium are tuned for each independent Lakeshore probe station model. And that's actually captured in the test definition itself. The driver is going to check that the sample stage has reached the final temperature, desired temperature, and that the stage is settled. The driver includes a device thermalization time. And so once the sample stage has reached the desired temperature, we allow the user to wait any number of minutes for the device to come into thermal equilibrium. So for many semiconductor applications, the thermal conductivity of the device is low enough that the substrate thermal conductivity is low enough that the device channel itself oftentimes needs a wait time. So we've included that in the driver. And finally, once the sample stage has reached equilibrium at the final temperature, our driver basically releases control back to the B1500 to use any number of the other test definitions to do the device measurement. Those drivers are going to be available from the lakeshore.com website starting here in the second quarter of 2016. So visit lakeshore.com to find the drivers for your specific probe station. Now, what an automated measurement looks like, it's fairly straightforward using the quick test option in the Easy Expert software. So what you see here is basically a combination of go to temperatures followed by an IDVG test definition, a transistor measurement. And so what we have here is basically a stack of temperature device measurements. It can easily be put together using that quick test tab in Easy Expert software. Now, for folks who have a little bit more programming experience or have some complicated variable temperature or variable field testing algorithms that they'd like to use, Lakeshore drivers can be called from within Easy Expert's built-in programming tool. So complicated measurements can be put together using that tool. So we go back to our quick test measurement. This is actually a selection of pHEMT results that came from that variable temperature quick test. So several IDVG curves taken from 30 Kelvin up to 290 Kelvin using our CVD probes and the Lakeshore temperature driver. And so for a fixed, VDD drain source voltage, what we see over temperature is here a reduction in the drain current, as well as a shift as the device is cooled of the pinch-off voltage. Both of these kind of point to the free carrier concentration in the active area of the pHEMT device getting smaller as we cool the device down. Now, one of the concerns for doing DC measurements in a cryogenic environment is actually this potential for ohmic heating of the devices. So one of our future developments that we'd like to integrate into our B1500 and temperature measurement protocol is the ability to do time-gated IV measurements. And so selecting cables, probes, and the appropriate acquisition parameters to do these pulsed IV characterization of the device and have good correspondence between the DC and the pulsed measurements. So keep an eye out for that in the coming years. So beyond doing transistor measurements, another application is using sheet resistance and the van der Pol method to measure not necessarily devices, but two-dimensional semiconductor material. This is again a low current application which can benefit from the triax cabling offered in Lakeshore Probe Station. Now the van der Pol method, can be used for an arbitrary shaped device, but typically we have square materials. Now the van der Pol method requires that small contacts are used, and typically we expect that a user is going to put on the appropriate metallization pre-applied to the material, and then the probe is going to make contact to the device. The van der Pol method, the contacts have to be on the circumference of the sample. The sample has to be homogeneous in thickness and no isolated holes in the sample. I will mention that EasyExpert has a van der Pol square test definition, which can make this a little bit more straightforward. To extract the sheet resistivity or the sheet resistance of your device, after doing the resistance measurement on two different geometries, so switching the current and voltage, the applied current and the voltage measurement on your van der Pol square, we invert the van der Pol equation there to pull out the specific resistance and then the sheet resistivity of the material. Now we recommend for cryogenic applications and getting a more complete result. And so for us, that includes doing current reversal. And so rather than just applying a current from terminal A to terminal B, we in fact reverse the current direction, and so the positive current direction will be from B to A, and then expect the corresponding change in the sign of the voltage. The second aspect of getting a more complete result, especially for cryogenic applications, is adding the second geometry. And so in addition to the two geometries shown at the left of the slide, actually rotating each of those, or flipping each of those so that the second geometry is measured, and then averaging those results. Both of these extra steps are going to remove offsets, thermoelectric offsets particular, that can show up in cryogenic van der Pol measurements. Now, a real challenge for doing sheet resistance measurement, van der Pol measurements in cryogenic probe stations is the idea of ohmic contacts. And so a lot can happen as the semiconductor material can change over temperature. The probes themselves can absorb and become non-ohmic along the way. And so what we recommend in doing a sheet resistance measurement is the idea of adding an ohmic contact step. And so this is the idea of adding an IV sweep where we basically source current from the corner-to-corner contact and measure the voltage along that same direction. So you use built-in test definition to do that. And so what you see at the right there is the idea of an ohmic contact. And so using the Pearson's correlation there, we get a correlation of 1. Now for a good ohmic contact, we expect at least 5 nines, but we can live with a correlation down to 4 nines. Anything below that we would consider to be a non-ohmic contact. So what we show there is actually, again, for a different set of contacts, the non-ohmic case. And so those contacts can either be rectifying or self-heating. So particularly at cryogenic temperatures, the self-heating is going to cause the carrier concentration and the resistivity of the material to change, not because of the material itself, but because of the contact. Now, when faced with a non-ohmic contact, there's a few directions that a researcher can go. First is to reduce the current if possible. If the voltage noise in your measurement allows for that, reducing current is really a good first step. And then correspondingly, you want to use that lower current in the van der Pol measurement. Another place to look is to lift and reland any of the offending probes. Just remember that these contacts at low temperatures the contact resistance can change and vary widely depending on the environment, the quality of vacuum, and any number of things. And so finding new ground to land your probes onto can help with non-ohmic contacts. And finally, considering the metallization to the semiconductor. And so not all cases do we get good ohmic contacts during the metallization phase. And so taking a look at those either through annealing steps or using different metals can change those contacts. Now the application where we're using sheet resistance is this idea of persistent photoconductivity. So we're measuring the change in the sheet conductivity as light is applied or shown onto a device, but the persistent comes in the case that for some materials the sheet conductivity is slow to recover once the light is turned off. And so you see a picture of the apparatus using our cryogenic probe station. So we're using a low-cost laser diode to illuminate the sample through the top optical windows of the probe station. Alternatively, you can use our fiber optic probes and a fiber optic coupled light source to do these measurements as well. Now, persistent photoconductivity is particularly well suited for wide bandgap oxide materials. So in these materials, basically the light is going to ionize any oxygen vacancies and increase the conductivity of the material. For these measurements, you see we measure the sheet resistivity as a function of time, and that ionization recombination rate of the oxygen vacancy is basically tied to the vacancy density as well as temperature dependent. Once we've acquired this kind of data, we can fit with the stretched exponential and pull out the material properties from that. These are pretty long time scale measurements, and so for this particular piece of tin oxide we're showing the graph on, this is a multi-day measurement, and so the cryogen-free probe station systems are well suited for these applications. Finally, because many of these oxides have low annealing temperatures, annealing stages as well as the changes in conductivity that come with annealing can be done in situ in a probe station. So this is a new application that we've been exploring here at Lakeshore, and we're really excited about some of the possibilities of using our probe stations for measuring persistent photoconductivity and a number of these emerging wide bandgap materials. Final application that we'll be talking about today is the capacitance-voltage measurement. Now, CV curves were initially developed to measure doping profiles in semiconductors, but since that time, it's become a valuable tool for basically understanding gate interfaces and transistors and the interfaces, oxide semiconductor interfaces, and MOS capacitors. Temperature dependent, because this is the valuable tool looking at the interface, the addition of temperature dependent characterization allows us to look at how defects affect the CV curves over temperature. The example we'll give you today is that of silicon carbide MOS structure. It's shown there. We've mounted our silicon carbide MOS onto a copper base, and then we probe the copper base, and then as well the 900 micron diameter aluminum electrodes. Because it's an aluminum electrode, we've chosen to use a tungsten tip, which is efficient at punching through the native aluminum oxide layer that can form on the aluminum electrodes. The 300 Kelvin CV results are shown there on the right, and shows good correlation as we change the frequency of the CV measurement. Now, to do these measurements in a probe station, see the picture at the right of the actual probing environment for the CV measurements. We did these measurements in our model CPX vertical field probe station. We use micro-miniature coax cables for these measurements. As I said, the 25 micron tungsten probe is important for the aluminum contacts. And finally, the measurement is done using the Keysight V1500A with the multi-frequency capacitance measurement unit. Now, what is typical for device-level CV measurements is this S2T configuration. That is a shielded two-terminal configuration. One of the key aspects of doing a good S2T configuration is this linking of the coax ground as close to the device as possible. This reduces the cable inductance, the effective cable inductance, reducing the overall measurement error. It's important to note that during a variable temperature CV measurement, to do short open cable compensation at every temperature. So as we change the temperature of the probe station, those cables are changing, and so the cable resistance and inductance is changing over temperature. And so for the cable compensation measurement, we use a 50 nanometer thick gold film on glass as a good short. That gold film offers low contact resistance for the probes and can help with good repeatability of the measurement. Now, we look at the temperature-dependent CV results that we measured for the silicon carbide MOS capacitor. Basically, a really drastic shift in the CV characteristic as the temperature is lowered. That flat band condition moves to positive gate bias as the device is cooled. Now, cooled to a point. So below 50 Kelvin, we actually start seeing the effects of carrier freeze-out in silicon carbide material. And so we no longer have the CV characteristic, but in fact, complete carrier freeze-out by 4.2 Kelvin. Now, one of the reasons, in addition to just seeing that temperature-dependent shift, cryogenic temperature CV measurements can be important for looking at the defects and trap states that are seen in these materials. So what you see at the graph on the right there is at 300 Kelvin, our CV characteristic has very low hysteresis. So as we scan the applied bias voltage from negative to positive bias, and then correspondingly from positive and negative bias, we see good repeatability of that measurement. Now, as we showed before, the CV characteristic is going to shift to positive bias as we cool down. But additionally, we're going to see a hysteresis loop in our CV result there. And so because of the clockwise hysteresis that we see in the CV measurement, this is really indicative of surface state traps in the MOS structure. Additionally, we did some variable frequency measurements. And so at low frequency, the CV curves are fairly smooth. But as we look at higher frequency or 1 megahertz CV characteristics at low temperatures, we see additional structure in the depletion region of that CV measurement. And perhaps this is an indication of fast interface states interacting with some interfacial traps in the MOS structure. This is some fairly new results, and we're very interested to see where those results take us. Now, one of the directions that those are going to take us is to higher frequencies. And so a future development for our cryogenic CV measurements is moving to higher and higher frequencies. Now, if you're familiar with CV measurements, load compensation is critical for reducing the error in the high frequency measurement, as shown by the graph there. Now, the challenge for including this load compensation into a cryogenic CV measurement is that resistor values change over temperatures. And so the plot we show there is for a trimmed, well-defined carbon resistor. And even for a high-quality resistor like that, we're seeing a few percent change in the resistance, which is going to propagate as errors in the CV compensation. And that brings us to our summary. So in today's presentation, we talked about temperature-dependent characterization and how that's important for device research and development, looking particularly at transport properties and defects. Then we looked at why we use probe stations for on-wafer characterization and many of the benefits of doing that. We introduced you to the cryogenic probing platform offered by Lakeshore. And finally, we looked at a few applications using the Keysight B1500 for these various device and materials characterization. Those included transistor IV measurements, the van der Pauw, and persistent photoconductivity, and finally CV characterization. It's a really good question. So in our standard configuration of probe station, the largest size is a 4-inch wafer. Now with some concessions in your probing area and thermal performance of the probe station, we can accommodate larger wafers up to about 6 inches. So the driver only determines that the sample stage is stabilized. There's a little bit of research that has to go into a little bit of development on the user side and understanding how their device is going to change, how long that takes for the device to come into equilibrium. So one of the recommendations that I can make in a case like that is actually two. One, we offer what's called a reference chip. So this is a calibrated sensor that sits on a substrate. And so depending on how you want to attach your device to the sample stage, you can attach the reference sensor in a similar way and then watch the thermals that way. The second thing we recommend is during kind of the development stage of your measurement is going to temperature and then doing repeated device measurements. And so you want to make sure that your device measurements are consistent, and once that happens, you have equilibrium. So you can get a good feel for that equilibrium time, and then for one device, and then kind of apply it to a larger, sampling of devices. All right, so we actually offer two different orientations. The first is a vertical field option. So in vertical field, the magnetic field is perpendicular to the wafer. We also offer some horizontal field options, one of which is our EMHF. So that uses basically a electromagnet, and with one option, the EMHF, the field is along the plane of the wafer. Now we have an option where you actually can rotate the device. So you have to lift the probes, but then rotate the device. And so the direction of the magnetic field relative to, say, the device channel on a transistor can be changed. In our flagship station, the CPX, it's a flow station. You actually can get from room temperature down to base temperature in around an hour and 15 minutes. That same station takes around 70 minutes to warm back up from base temperature. Now, the larger systems are going to take a little bit longer. The systems with the integrated vertical field magnets, because of the heat capacity of the magnet, it take a little bit longer to cool down and longer to warm back up again. So it really does, the tip itself is going to sit somewhere between 10 to 15 Kelvin in most of our probe stations. We can tie that probe directly to the sample stage, and so the offset between the sample stage and the probe tip can be a few Kelvin. But again, the probes themselves are going to see a little bit higher radiative heat load than the sample chuck, just based on how they're set up. And so the device temperature tends to range between the sample chuck and the probe tip temperature. So typically the DC probe itself, the probe arm temperature, we like to limit below around 350 Kelvin. We've taken those a little bit warmer as well, but at some point those probes themselves, the electrical properties are going to start changing as they get hot themselves. So our vertical field magnets at the conventional standard probing position it's around 2.5 Tesla. We have an additional option where we can actually drop the device into the solenoid of the vertical field magnet and get fields as high as 3 Tesla. Now to do that, we have to have special probes to accommodate that geometry, but 3 Tesla is certainly nothing to sneeze at from a device scale measurement. The horizontal field measurements, those typically run a little bit more than half a Tesla. Sorry, in the horizontal field electromagnet configuration. So in our CPX probe station with the ultra low temperature option, the chuck temperature is as low as 1.6 Kelvin. Yeah, actually, in the HEP results that the pHEMT results that we showed today, when we first started testing those, we did get oscillations. I mean, it's a transistor, and as you're changing the semiconductor material, those oscillations can actually get a little bit worse as you because of the changing resistivity of the channel. What we ended up doing in this case actually was just lower the drain source current, or the drain source voltage, and as well as some of the gating options. And so I think the takeaway there is that your electrical parameter space is going to change as you cool the device down, because the device fundamentally from a physical and materials standpoint is changing. We offer, I think, like 3 different kinds of probe tip material. So for delicate, softer materials, I'd recommend our beryllium copper probe. It offers conventionally the lowest contact resistance and basically the smallest amount of damage to the contact metallization. For things, as we discussed during the presentation today, contacts like aluminum and other materials that develop oxides, that's where you have to use that tungsten probe to punch through the oxide material. Now, halfway in between kind of those 2 performance materials, we have a line of Pauw probes, and so, or Pauw probes, depending on how you pronounce that. But the Pauw probes offer low contact resistance, but a little bit stronger of a material, so kind of a halfway option. So again, thanks again for listening to the presentation. For more information regarding Lakeshore cryogenic probe stations, please visit www.lakeshore.com, and your keyword there is cryogenic probe stations. If you're interested in more information on the B1500 semiconductor device parameter analyzer, visit keysight.com, and your search term is B1500A.